In this video, I will teach you how to find intervals of concave up and concave down given the equation of f of x. If you appreciate the content, please give it a like. So much of what we do in AP Calculus relies on these graphical relationships between f, f prime, and f double prime. Make sure you know them so well that you can write this chart from memory in the margin of your next test or quiz. Today's lesson is all about finding intervals of concave up and concave down for the original function f. According to our chart, wherever f double prime is positive, f will be concave up, and wherever f double prime is negative, f will be concave down. In other words, if f double prime at a is positive, then f of x is concave up at x equals a. If f double prime at a is negative, then f of x is concave down at x equals a. If f double prime at a is 0, all we know about f is that it is neither concave up nor concave down. That might mean that f has a point of inflection at x equals a, where f changes concavity, but not necessarily. If f double prime at a is undefined, all we know for sure about f of x is that it is not twice differentiable at x equals a. These two statements actually mean the exact same thing. Obviously, if you can't take the derivative twice, then the second derivative is undefined. Notice that if f double prime changes signs at x equals a, that means f of x definitely has a point of inflection at x equals a. Think about it. We know that if f double prime is positive, f of x is concave up. If f double prime is negative, f of x is concave down. So obviously, if f double prime changes signs, then f of x changes concavity. For example, if f double prime changes from positive to negative, then f of x goes from concave up to concave down, thus a point of inflection. Before we move on, I want to say a word about abbreviations. In other videos, you will often see me use these abbreviations for concave up, concave down, increasing, decreasing, positive, negative. Of course, I accept these abbreviations in my class, but I want to be clear. You are taking a risk when you use any abbreviations on the AP exam. That's because it's up to the discretion of the grader whether or not they're going to accept it. Now, most AP graders are going to give you full credit for these abbreviations. However, there are hundreds of AP graders, and there are a few who won't give you credit for these. So if you want to be 100% safe, do not abbreviate at all on the AP exam. However, if you're pressed for time, it might be worth the risk. There are two ways to define a point of inflection. Of course, a point of inflection is where f of x changes concavity. However, this is the definition that we use most often in calculus. A point of inflection is where f double prime changes signs. So if I were to stop you in the street and ask you, hey, what's a point of inflection? I want you to say, well, that's where f double prime changes signs. Let me show you how to structure your justification for intervals of concave up, intervals of concave down, and the existence of a point of inflection. f of x is concave up on the interval from a to b because f double prime is positive. Notice that we always use parentheses, not brackets, for intervals of concavity. F of x is concave down on the interval from a to b because f double prime is negative. And f of x has a point of inflection at x equals a because f double prime changes signs. The big idea is that the sign of f double prime tells you the concavity of the original function f of x. Here are the steps for finding intervals of concavity or points of inflection. Step 1. Find f prime. Step 2. Find f double prime, the derivative of f prime. Step 3. Find where f double prime is equal to 0 or where f double prime is undefined. Technically, these values are the critical values of f prime, but nobody calls them that. We usually save this phrase for when we're talking about the critical values of f, and that would be where f prime is equal to 0 and where f prime is undefined. Step 4 is to make an f double prime sign chart. This will show us where f is concave up or concave down. We will also be able to recognize any points of inflection where f of x changes concavity. Let's try an example. Discuss the concavity of the function y on the interval from 0 to 2 pi and find the x-coordinates of any points of inflection. Step 1 is to find y prime. The derivative of x squared is 2x. I see a constant coming, so I'm just going to bring that down. The derivative of cosine is negative sine x. Don't do like this. Instead, I want you to take that negative sign and put it in the very front. So I'm going to put sine x right here, but because it's actually negative sine x, I'm going to switch this to a negative. The derivative of a constant is 0, so this is y prime. Next, we find y double prime by taking the derivative of y prime. The derivative of 2x is 2. Bring down the constant. The derivative of sine x is cosine x. So that's y double prime. Next, it's time to find the critical values of y prime, where y double prime is equal to 0 or where y double prime is undefined. Y double prime is a transformation of the cosine function, which is defined everywhere, so we don't have to worry about where y double prime is undefined. So we just set y double prime equal to 0 and solve. Adding 4 cosine x to both sides, we get 2 is equal to positive 4 cosine x. Dividing both sides by 4, we get 1/2 is equal to cosine x. I'm just going to flip these around. Where does cosine equal 1/2? Hopefully you memorized these 9 trig facts long ago, including the fact that the cosine of pi over 3 is 1/2. That tells us that the reference angle is pi over 3. A reference angle is the angle between the terminal side and the x-axis. Every quadrant has an angle with a reference angle of pi over 3. However, cosine is the x value on the unit circle, and x values are positive on the right-hand side and negative on the left-hand side. In this case, we want cosine to be positive 1/2. So we will disregard these two potential solutions. So on the interval from 0 to 2 pi, the two solutions are pi over 3, the reference angle itself, and whatever this is. If we went all the way around and back to the start, that's 2 pi, and we can think of that as 6 pi over 3. So pi over 3 before that would be 5 pi over 3. So those are the two solutions. Now we make an f double prime sign chart with the critical values in order from least to greatest across the top. Be sure to include the domain limitations 0 and 2 pi. Also be sure to label your chart as f double prime. This is an important part of showing your work. We need to decide whether f double prime is positive or negative in each one of these intervals. So we need to pick a test value in each interval to plug in to see if f double prime is positive or negative. On this first interval, we are allowed to use the value of 0 as a test value. Even though it's not technically included in the solution set, that doesn't matter. We can still use it. Plugging in 0 for x gives us this expression. What is the cosine of 0? Cosine is the x value on the unit circle, and at 0 radians, the x value is 1. So this is 1 right here. So really, you can ignore this because 1 times negative 4 is still negative 4. So this is really 2 minus 4, which is less than 0. It is negative. So f double prime is negative in this interval. Next, we need to pick a test value between pi over 3 and 5 pi over 3. That means we can use any of these values right here from pi over 3 all the way around to 5 pi over 3. So there's a lot of great ones to use, but why not use pi over 2? Because the cosine of pi over 2, the x value, is 0. Very convenient. Plugging in pi over 2 gives us this, and as I said, the cosine of pi over 2 is 0, which wipes out this whole term, leaving behind simply 2, which obviously is greater than 0. It is positive. So f double prime is positive in the middle interval. On the last interval, we can use 2 pi just like we used 0. But I'm not even going to write this down because obviously the cosine of 2 pi and the cosine of 0 are the same thing. So we're going to get the same value. So f double prime will be negative again on this interval. Our sign chart only had one row, so these signs indicate the overall sign of f double prime in each interval. Small correction, I've been calling it f double prime, but this is y double prime. And we can use the y double prime sign chart to discuss the concavity of the function y. Wherever y double prime is positive, y is concave up, and that's going to be on the interval from pi over 3 to 5 pi over 3. We say y is concave up on the interval from pi over 3 to 5 pi over 3 because y double prime is positive. Y will be concave down wherever y double prime is negative, and that's on the interval from 0 to pi over 3 and 5 pi over 3 to 2 pi. We say y is concave down on the interval from 0 to pi over 3 and 5 pi over 3 to 2 pi because y double prime is negative. We can also identify where y has any points of inflection because a point of inflection is where y double prime changes signs. And we see that y double prime changes signs here at pi over 3 and here at 5 pi over 3. We say y has a point of inflection at x equals pi over 3 and x equals 5 pi over 3 because y double prime changes signs. Pause the video and try this example on your own. On the interval from negative pi to pi, find the intervals on which the graph of y is concave up and the intervals on which it is concave down. Also, find the x-coordinate of any points of inflection. Step 1 is to find y prime, but the first term of y is a product. So watch out. We have to do the product rule. Do not think that you can take the derivative by just taking the derivative of x and the derivative of cosine and smashing those together. You have to do the product rule. The product rule says that you go through this twice, and the first time through you take the derivative of the first factor. The derivative of x is 1. The first time through you leave the second factor unchanged. So you bring down the cosine x, and then you put a plus and you go through it again. The second time through, you leave the first factor unchanged, and you take the derivative of the second factor. The derivative of cosine x is negative sine x. Now don't do this and put negative sine x like this. Students often get confused and wind up doing subtraction when it should be multiplication. So instead, whenever you are multiplying by a negative, I want you to put that negative in the front of its term, which in this case is going to be right here. So that was it for the product rule. Moving on to the next term. When you see a constant, you just bring that thing down. And then you go ahead and take the derivative of whatever comes next. The derivative of sine x is cosine x. So this is y prime. We should simplify this before trying to find the second derivative. These are like terms. 1 cosine x minus 2 cosine x is negative 1 cosine x. Now we can find y double prime, the derivative of y prime. But the first term is, again, a product. So we have to do the product rule. According to the product rule, the first time through we take the derivative of the first function. the derivative of negative x is negative 1. The first time through, we leave the second factor alone. So I'm going to bring down the sine x, and I'm going to put a plus. And now I'm going to go through it again. The second time around, we leave the first factor alone. So I'm going to bring down the negative x. Now that I see that it's a negative x, I'm going to just let this be negative. So there's my negative x. But then I take the derivative of the second function. The derivative of sine x is cosine x. So that's it for the product rule. Moving on to the last term, bring down the negative sign, and then take the derivative of cosine x. That is negative sine x, but obviously we're not going to put minus negative sine x. The second negative will turn the first negative into a positive. I'm noticing that we have like terms again. Negative sine x and positive sine x cancel each other out. So y double prime is equal to negative x cosine x. Now it's time to find the critical values where y double prime is equal to 0. Normally we would also consider where y double prime is undefined, but cosine is defined everywhere. So let's just take negative x cosine x and set that equal to 0 and solve. We can solve by setting each one of these factors equal to 0 separately. Dividing by negative 1 gives us x equals 0 for the first critical value. But be careful here. Normally we think cosine is equal to 0 at x is equal to pi over 2 and x is equal to 3 pi over 2. But that's because we are used to the interval from 0 to 2 pi. But that is not the domain we were given. We have the interval from negative pi to pi. This is actually going to be the entire circle, but negative pi is from here to here. And positive pi is from here around to here. Pi over 2 is fine because pi over 2 is right here between 0 and pi. But 3 pi over 2 is beyond pi, and that's outside of the domain. So to get to this position, which we normally call 3 pi over 2, we need to go this way. So that's going to be actually negative pi over 2. Build a sign chart putting your 3 critical values in order from least to greatest across the top. Be sure to include the domain limitations, negative pi and positive pi. Also make sure to label the sign chart as y double prime. This time we should have 2 rows. We should have a row for each factor, one for negative x and one for cosine x. We need to decide whether negative x is positive or negative in each one of these intervals. Remember, negative x is equal to 0 at 0. So this is the only place where this factor might change signs. If we plug in any values to the left of 0, negative values, we will have a negative times a negative, which is a positive. So negative x will be positive on the left of 0 and negative to the right of 0. Cosine x is equal to 0 at negative pi over 2 and positive pi over 2. So these are the only 2 places where cosine x might change signs. So we don't have 4 intervals to check. We really only have 3, left, middle, and right. We're going to do test values like we did before. For the first interval, let's go ahead and use negative pi as the test value. If we plug in negative pi, that's going to be cosine of negative pi. And negative pi is on the left of the circle where cosine is negative 1. So cosine x is negative 1 in this interval. I'm going to jump ahead to this interval because positive pi and negative pi are in the same position on the unit circle. So either way, the cosine is going to be negative 1. On the interval from negative pi over 2 to positive pi over 2, we can use 0 as a test value, and we can do this mentally. The cosine of 0 over here on the right-hand side of the unit circle is 1, positive 1. So cosine is positive in this interval. A negative times a positive is a negative. A positive times a positive is a positive. A negative times a positive is a negative. And a negative times a negative is a positive. Y will be concave up wherever y double prime is positive. That's from negative pi over 2 to 0 and pi over 2 to pi. We say y is concave up on the interval from negative pi over 2 to 0 and from pi over 2 to pi because y double prime is positive. Similarly, we say y is concave down on the interval from negative pi to negative pi over 2 and on the interval from 0 to pi over 2 because y double prime is negative. The function y will have a point of inflection wherever y double prime changes signs. We notice that y double prime changes signs here, and here, and here, so basically all of the critical values. We say y has a point of inflection at x equals negative pi over 2, x equals 0, and x equals positive pi over 2, because y double prime changes signs. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.